Example 186. Researchers measured the bursting strength of two different bottle designs, the old bottles versus the new. At the 5% significance level, test the claim that the probability distributions associated with the two bottle designs are equivalent. Okay, so we're looking at some bursting strength numbers for the two types of bottles, and we want to basically make this comparison using the Wilcoxon ranked sum test for independent samples. So the sample sizes are small, and there's no mention that anything is normally distributed in here, and they're asking us to test the claim that the distributions are equivalent, and we have two independent samples. We know they're independent because they're two different groups of bottles, two different types of bottles are looked at here. Now, if you look at the notes that I have included with this video, you'll see that in the notes I use the expression that they use here. So it says test the claim that the probability distributions associated with the two bottle designs are equivalent. If probability distributions are equivalent, what they're getting at here is that they have the same central tendency, or in other words, they have the same location on the number line. They also, of course, as a broader statement implying that they have other things in common, like, for example, they have the same variation or spread in the data, etc. But what I want to do mainly is express the claim in a different way than I did from the notes to see the two different alternatives. So what I could do instead of using the method I used in the notes is I could actually talk about the medians, right? I can say, hey, look, the median for the old bottles should be equal to the median of the new bottles. And why would this be true? Well, if they're equivalent, if the probability distributions are equivalent, then the medians would be in the same location. So we could basically boil that expression down to a statement about the medians. So that would be okay, right? It's a more narrow claim. And then let's look at HO and HA as a result of that. HO, of course, matches the claim here because the claim has an equal to sign. So I'll just kind of recopy that down. And then, of course, for HA, we have the opposite idea, which is not equal to, right? So not equal to for the other one. Okay, now the next step that we're going to do is we're going to actually take some time here to rank the data. This is the data step. When you work with the data in step 3, right? Claim step 1, hypothesis step 2, then we rank the data in step 3. So, step 3 throughout this course has been the step that I designated for kind of manipulating the data or working with the data. And so in this case, we're going to be finding the ranks. And finding the ranks for a long list of numbers like this is kind of difficult. You have to be very careful. So let's go through very carefully and try not to make a mistake. And we're going to rank them, making the smallest number 1, and then the next smallest number 2, so on and so forth. So I'm going to quickly scan the list. And I see lots of numbers in the 200s. So that means that things in the 100s would probably be kind of on the smaller end of things. So this 164 could be a candidate for the smallest number we have. It's not, though, because I look below and I see that I have 162, 137. That's real low, and then I have 150s and 170s. So I'm going to go with 137 as being the lowest number in my list. I'm going to call that 1, give it rank 1. Okay, so now that I've given that rank 1, I'm going to move on to the next number. Now, I did see numbers that were in the 150s. Anything else like in the 140s? I don't think so. So it looks like 152 will probably get rank 2, and 153 might get rank 3, right? Okay, good. And then from there, is there anything else in the 150s? I don't see anything else in the 150s. How about 160s? Well, there's a 162 here, and above there's a 164. So maybe we can give this ranks 4 and rank 5, right? Okay, now once we have the 160s laid out, let's look at 170s. Anything in the 170s? Nothing in the first row, but there is a number here in the second row. That gets rank 6 then. All right, how about anything in the 180s? I don't see anything else in the 180s. There is a 190 though, so that's going to get the next rank, which is 7, right? So we have 1, 2, 3, 4, 5, 6, 7 so far. And now anything else in the 190s? I don't see anything else in the 190s, so now we're in the 200s, just the 20 something, right? All these are in the 210s, or there's a 209, that's pretty small. Anything else then? Nope, that's the next number then, so that's going to get rank 8. And then we're going to look for things in the 2 teens, like so 210, for example, would be one of them. So there's one 210. Are there any other 210s? No. So I'm going to go ahead and give that rank 9. Now 211. Okay, so I see several 211s. I got one here, one here, one here. Lots of 211s. So here's what you're going to do with the 211s. You're going to go ahead and, so this is rank 9. I'm going to give this rank 10, rank 11, and rank 12. But I'm going to circle those ranks. And I'm going to use a round circle, specifically a circle. Whatever symbol you use, whether it be a square or a circle, stick with it, right? Or use a different color pen or something. Because you want to remind yourself that later on you're going to have to go back and correct these because these are ties and they can't remain different ranks like that. Since they're all 211, they have to have the same rank. For now, we're just going to call them 10, 11, 12 so we don't make any mistakes. All right, so now 212 would be the next number there. So there's a 212 here. There's also a 212 here. So I'm going to give this rank 13 and give this rank 14. Any other 212s? No. Now for 13 and 14, I'm going to use a rectangle to circle those. Not a circle, a rectangle, so I know that those are the same. It'll just be a visual reminder of that for later. Then anything like 213 would be 15, right? So I'll give that 15. Is there any other 213s? No. Is there a 214? There is, so that would get 16. Are there any other 214s? No. So then I'll say, okay, next number is 215. No, there's no 215s. There's a 216 though. So I'm going to go ahead and give that rank 17. Then we should have rank 18, rank 19, and rank 20. Now, at the end of this initial phase of ranking, we should have, our last rank should be the same as the number of values we have, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns, each with 2 numbers in it, so there's 20 numbers. That last rank I give out had better be 20, and it is, so that's good. Now let's go fix the ties. We had ties, we have to now make sure that those ties don't remain different values. So what we're going to do for the ones with the circle, we're going to say, hey, look, these are all the same, so if I average them, if I add 10 to 11 to 12 and divide by 3, I will get 11, right? If you want to check that, of course, you can do it in your calculator if you need to. You can say 10 plus 11 plus 12, enter, and then divide by 3, and of course, as I promised, you will get 11. So that means we're going to cross this out, and we're going to give each of these rank 11, right? So each one gets rank 11. Now I know I've taken care of all of those. Now let's look at the one with the square. For the one with the square, we would add the 2 numbers together and divide by 2 because there's only 2 of those in the square. So 13 and 14 divided by 2 is going to give you 13 and a half. So for each of these, I'm actually going to use 13 and a half. Okay, so that is how you finish your ranking. Your ranking is fully done. Now you're left with the next phase of the problem. The next phase of the problem is to add up those ranks, and that's going to give you your candidates for your test stat. So there's a rule. It says that the smaller sample size row will become your test stat. So its rank total will become your test stat. So if you look at this row, it has 10 values in it. If you look at this row, it has 10 values. So we don't have a smaller sample size for either row. Both rows, both types of product here, the old design and the new design, they each have 10 values associated with it. So the rule normally is that your test stat will be the sum of the ranks for the row that corresponds to the guy that has the smaller sample size. But they have equal sample sizes here. So what we're going to do is just pick either one to be our answer. So for example, I could take the first one, the first sum, to be our answer. So let's say our first test stat here. Our first test stat, we'll call it T1, the rank total for the first group or first population. Let's add up the first row's ranks, and that will be my test stat for this problem. Okay, so now we're on to step 4 of the test stat. We're going to say 9 plus 13.5 plus 11 plus 11 plus 7, right? Plus 15. I'm just adding the ranks up, just the ranks themselves, not the numbers, right? 13 and a half. Added to 11, added to 5, added to 8. Okay, so if I add up all those ranks, I get 104. Now, the other rank total down here should sum up to a value that's going to be the same as 20 times 21 divided by 2. So there's a little rule in mathematics that says if you add up the digits from 1 to n, the sum will be n times n plus 1 over 2. And so what we're going to do here is essentially say, well, if I want to check, I can make sure that the sum of this row added to this thing is going to give me that total product that I was looking for. So let's do that. Let's just check that. So I'm going to do 17 plus 16 plus 4 plus 1 plus 20 plus 19 plus 6, right? Plus 3, plus 2, plus 18. Okay, so if I add up all that, I get 106, right? So we'll say that T2 the rank total for the second row is 106. If I add those together, of course, I'll get 210, right? What is 20 times 21 divided by 2? You get, of course, 210. And that has to be true. If these don't sum up to that total, then you've done it wrong, right? So where did I get the 20 from? Because there are 20 values total here. That means the rank sum, if you add up all these ranks that I gave the numbers, they should add up to the number 20 times one more than that, which is 21, divided by 2. And that's a quick check to make sure you did it right. Now let's let this guy be our test stat. Generally speaking, our test stat, again, it goes to the smaller sample size. In other words, if this row had only had 9 values in it, we would have made this our test stat. The rank sum would have become our test stat. But since there's equal sample sizes for both, it doesn't matter which one I make our test stat. I'm just choosing the first one. Arbitrary choice, it doesn't matter which one we choose. So since this doesn't matter, I'm arbitrarily choosing rank total for the first group as being our test stat. Okay, so this guy will become our test stat, and now we have to look at our critical value. In order to look at your critical value for this problem, what you're going to do is you're going to say, okay, this is the Wilcoxon ranked sum test, right? So we ranked all the data, then we summed up the ranks, and that's what our test stat became. We're going to go to the table for that, and we're going to look up the sample sizes in the problem in order to come up with our critical value. We also want to look at our alpha and the type of test we're conducting. So for the critical value, here's what we're going to need for the table. For the table, we're going to need the fact that we have a 5% significance level, right? 0.05, and then we're going to need to know how many tails we have. Based on HA, this is a two-tailed test because a not equal to symbol means two tails, right? So two-tailed test. Okay, so 0.05 for alpha, two-tailed test, and then the sample size. N1 is equal to 10 and N2 is equal to 10. In other words, there were 10 values in each row of data that we had. Okay, armed with this information, let's go to our table and find our critical values. Okay, so in this problem, we're looking at 0.05 for a two-tailed test on the Wilcoxon rank sum table. So 0.05 two-tailed test. That's going to give us 0.05 two-tailed test. We're in this first cell, and then we see that the n for both samples was 10. So we're going to line that up for n1 10, n2 10. We actually find the intersection to be here. So our two critical values are 79 and 131. So our TL is 79 and our TU is 131. Okay, so we found the answer for the critical value to be 79 and 131. This guy is referred to as TL, or in other words, the lower value, and then TU, which is the upper value. And the way we want to think about these critical values is very simply, we want to draw sort of a number line and want to put them on that number line. So let's do that. So here's a number line. I'm going to put the number 79 on it, and I'm going to put the number 131 on it, right? So now here's what we're going to do. We're going to basically follow the procedure that if these test stats land inside this area here, right? If it lands inside this area there, or lands inside this area here, and we'll use a bracket here to include those values. So if we land in either of those areas, then we're going to say we should reject the null hypothesis, right? So here it'll be reject HO, here it'll be reject HO, right? So if our test stat ends up in either of these two pieces, we'll reject HO. But if it lands in the middle somewhere, we're going to say that we do not reject HO. So it's very similar to what we've done in the past. All right, now looking at our test stat of 106, you see that 106 is safely what? In here, right? 106 being inside sort of the middle range. So we're going to say that we do not reject HO. So finally, we conclude that we do not reject HO, we do not support HA as a result, right? Because we don't reject HO, we're saying HO is okay, so therefore we should not support HA. And since our claim is HO, we're going to be saying this in our final conclusion. So we want to word our conclusion where we say essentially, hey, the sample data does not allow us to reject the claim that the bursting strengths for the old bottle design and the bursting strength for the new bottle design have equivalent medians or have equivalent probability distributions. So that's basically the idea of the problem. Remember, this is a non-parametric procedure. Non-parametric procedures tend to be weaker than parametric procedures. And so because of that factor, or because of that issue, sometimes they have a harder time rejecting false null hypotheses. So it could be that this result is due to the fact that the power of the test is weak. But if you look at our ranks here, the ranks don't imply that, right? The ranks are very close to one another. So the idea behind this test is pretty simple. If one of the bottles had a much higher bursting strength, it would have all the big numbers in its row. And because it had all the big numbers, it would have all the big ranks, right? But you see these rank totals are almost identical, meaning there's very little difference between the bottles overall, it seems. And so for that reason, it seems like this is a valid conclusion that we shouldn't reject HO. We should say that essentially they seem to be equivalent. And that's the end of our procedure.